kind invitation. So I'm Marco Minissale. I'm a researcher at the CNRS, the PIM laboratory at the Aix-Marseille University. And as you can see in my the title, I will speak about the uncertainties in ice laboratory experiments. So first of all, I want to clarify what we can measure in the what we call the ice laboratory experiment. So it works? No. Okay. So what we measure? We can measure for example, here is a non-exhaustive list, some thermal activated process, for example, reaction rate, thermal desorption rate, or diffusion constants, or also some non-thermal activated process, for example, photo desorption yields or chemical desorption, electron-induced desorption. But how we measure this quantity and what we need? So the ingredients are, for example, the flux of atoms and molecules that we send on a surface. We have to know what is the temperature of this surface. We have to know, for example, if we study some induced a process by the flux of particles that we send on the surface, and this gives us a first source of uncertainty. So the calibration, this is systematic errors when we try to measure the flux of atoms, the sample temperature, and so on. Then there is another error that is what we call the instrumental error, that is given by how we measure the ingredient, what I call the ingredient. So for example, if we want to know the sample temperature, we can use thermocouple, or if we want to probe the particles in the gas or in the solid phase, we have to use some spectroscopy, as for example, infrared or mass spectroscopy. And we have some instruments that have some accuracy, and so we have some instrumental error given by this kind of measurement. So if we take an example of an experimental setup that used to study ice laboratory experiment, we see that the calibration and systematic error comes from the, for example, from the beam line, to send the atoms and the molecules to the surface. Then we have the instrumental error that comes from the instrument that we use, for example, the infrared spectroscopy. But then there is another source of uncertainty. So the two here are what we can call experimental uncertainty. But then we have to analyze and interpret our result. And so, as we already see, we have to do some hypothesis, some assumption about the model that we have. What are the parameters that we want to extrapolate from our result? What are the physical chemical processes at play during our experiment? So I will give you some two examples, if I have the time. One is some experiment that we performed to study the diffusion desorption properties of oxygen atoms on cold surface. And the second one is about the H2CO plus O reaction on solid phase. So about the first example, how we can measure the diffusion desorption properties by doing what I recall the TPD experiment. So is a temperature, the acronym means temperature programmed during exposure desorption. And the experiment is quite simple. We have a surface that we hold a certain temperature, for example, 100 Kelvin, and then we start to send atoms and molecules on the surface. For example, in this case, oxygen and O2. And with a quadruple mass spectrometer, we look to the gas phase, what desorbed from the surface after that we sent all the atoms and the molecules on the surface. So we have a certain level of noise that is given by the experimental uncertainty and the instrumental uncertainty, and we can start to interpret our result. So here you see, for example, a flat part of the curve that can be interpreted as the oxygen and O2 desorbed from the surface. Then we have a second part where we see the signal of oxygen that decrease and the O2 that increase, and so we can say that O2 start to stick on the surface, diffuse, and form O2 that, since the temperature is too high, will desorb, and this is the reason it rises. Then we have a third part where O2 start to stick, and so O3 can be formed, and so the O2 signal decrease. And finally, the third part where we have some flat region where all the reactants are on the surface. So we have an interpretation. Now we have to move to the modeling to get some information from the result. from the experimental result. So we have, I say that we have diffusion, we have desorption, we have also some reaction. So we can build a rate equation model where we have the coverage as function of the time. That is our experimental result. And we have some experimental parameter that is, for example, the flux or the coverage of on the surface. And then we have the parameter that we want to find from our experiment. The desorption rate is what we can measure, and so the activation energy for desorption, and here the diffusion, the activation energy for diffusion. By using this model, by fitting the TPD experiment, we can find the couple of diffusion desorption energy. And what we get is a kind of a plot of this type, where we have the diffusion energy as function of the desorption energy. What you see, this kind of bananas, are the value of the couple energy diffusion and desorption energy that minimize the deviation between our experimental finding and our simulation. But as you can see, for example, the diffusion here is quite, there is a quite a big error bar, because can go from 600 in the case of oxygen atoms on amorphous solid water, we can go from 600 to 1600 600 Kelvin. So in this case, we cannot really break the epistemic opacity, because we don't have any we don't have a better constraint or one of the two parameters. So once we can answer to this question, so which is the ratio that this ratio which is the most appropriate is 0.5, 0.7, 0.9. We can give some better, we can have some better constraint of the two parameter. And so, in other words, we need some inputs from other experiment to evaluate the ratio, or to evaluate one of the two parameters that are actually coupled. And if I have time, I will move to the other example that is quite similar, but is more on the reaction. So we want to study the H2CO plus O reaction. We know that this reaction work in a gas phase with this activation barrier, and at a certain moment we try to understand if the surface can play a catalytic role decreasing this activation barrier. But we have some issue, because when we study this reaction in gas phase, the presence of oxygen atoms makes harder the estimation of the activation barrier in solid phase, because first of all, from an experimental point of view, when we do this experiment, we don't have just oxygen atoms, but we have also a flux of O2 molecules. So we basically study H2CO plus O plus O2. And then there is some intrinsic properties of oxygen atoms that we have to deal with, that are the fact that oxygen atoms can diffuse quite fast on the surface, and also oxygen atoms can react each other. So we do our experiment again by using the temperature program desorption technique, where we see the presence of CO2 peak after the experiment and the consumption of H2CO. We can also do by infrared spectroscopy, and we can follow the kinetic of formation of CO2, but also the consumption of H2CO. And again, as in the case of that I presented just before, we have to do some model to try to interpret our result. And so we can try to separate the different processes, but we see that we don't study, when we study this reaction in solid phase, actually we study a more complex chemical network. So we study, for example, the formation of O2, the formation of O3, the consumption of H2, probably also the reformation of H2CO, and then finally the formation of CO2. With all this, the different parameter, for example, the AEA, that is the parameter that we want to get from our experiment. And as you can see, we have a certain amount of source of uncertainty, because we have, for example, parametric and experimental uncertainty about the flux of oxygen of O2, the initial coverage H2CO, but then we have some other parameters that are physical chemical parameters that are able to describe our experiment. And so if we know all these parameters, we can run the simulation and we can get the activation energy. But when we try to do the simulation, what we get is that actually we see that there are two coupled parameters. That is the activation barrier for H2CO plus O reaction, but also the oxygen diffusion. If we try to fit our experiment, we see that we can fit with a similar Q2 square our experiment if we use a 900 Kelvin diffusion barrier for diffusion of oxygen, but also if we use a 600 Kelvin. So if we don't have any clue about the oxygen diffusion, we see that the model uncertainty can count in our estimation of the barrier for a 30%, while the experimental uncertainty that is given by the what I say the estimation of the flux, the estimation of the coverage, it accounts just for 10%. And so I will finish just saying that as I explained, we have two kind of uncertainty. So the experimental uncertainty that can be easily taken into account, handled, can be estimated, and in some case can be reduced from an experimental point of view. But often the main source of uncertainty comes from the fact that when we study a system, we have coupled parameters, coupled process, and we cannot really separate the two in a simple way. And I think I finished. Thank you for your attention.